59 earthquakes have hit the same stretch of the San Andreas Fault in 6 days, running at nearly 7 times the normal rate for that patch of ground. On Tuesday morning, the sequence produced a magnitude 3.94, the largest event there in almost 15 years. And here's what makes it matter. It's happening on the one section of the San Andreas that isn't supposed to break at all. By the end of this, you'll understand why 4 meters of rock pulled from 3 kilometers underground quietly demolished that assumption. The San Andreas Fault has been producing earthquakes almost continuously since last Friday, and the place it's been doing it is the one stretch of that fault geologists have spent decades describing as harmless. The swarm is centered beneath Pinnacles National Park in San Benito County, Central California. It began on Friday, August 7th, with 2 magnitude 3.2 earthquakes about 78 minutes apart. It didn't stop. It ran through the weekend, escalated Tuesday morning, and was still producing events days later. In the tightly drawn box that contains the main cluster, the catalog holds 59 located earthquakes across 6 days. Nobody has been hurt, nothing has been damaged. No agency has issued a warning, an advisory, or an elevated alert of any kind. And none of them should have, because on the raw numbers, this sequence is small. The largest event in it would rattle dishes in Hollister and go completely unnoticed in San Jose. What makes it worth paying attention to is where it happened. The swarm sits directly on what seismologists call the creeping section of the San Andreas, roughly 150 kilometers of fault running from San Juan Bautista in the northwest down to Parkfield in the southeast. On this stretch, and only on this stretch, the two plates slide past each other continuously. They don't stick, build up strain, and release it in a single violent snap. They just move, day after day, at roughly the rate the plate boundary demands. That behavior is the entire reason. The standard answer to the question, could the whole San Andreas rupture at once, has always been no. The creeping section has been treated as a permanent barrier, a stretch of fault so lubricated, so incapable of storing energy, that a rupture arriving from the north or the south would run into it and die. Everything you've ever heard about the big one being confined to one half of California or the other rests on that assumption. 4 years before this swarm began, a group of researchers pulled rock out of a borehole at the southern end of this exact segment and found something that doesn't fit that assumption at all. We'll get there. First, the swarm itself, because the numbers matter and they're worth stating precisely. At 10:19 and 8 seconds Universal Time on Tuesday, August 11th, 3:19 in the morning. Pacific Time, a magnitude 3.94 earthquake struck 6 kilometers northwest of Pinnacles. Depth, 4.62 kilometers. 85 seismograph stations reported it. The azimuthal gap, a measure of how well those stations surround the epicenter, was 40 degrees, which is good coverage. Horizontal error, 14/100ths of a kilometer. That's not a preliminary automatic solution that might get revised by half a magnitude tomorrow. That's a reviewed, well-constrained answer. The fault did exactly this, exactly here. Within 3 minutes and 33 seconds, 3 more located earthquakes followed. A magnitude 2.57, a magnitude 2.60, and a magnitude 2.14, all within a few kilometers of the first. The largest event to follow anywhere in the rest of the sequence was a magnitude 2.66 about an hour and 50 minutes later at a depth of just 500 meters, the shallowest significant event of the entire swarm. By the end of that Tuesday, the catalog held 27 located earthquakes for that single day. Here's the first thing that's strange about this sequence. It got bigger as it went along. A classic main shock and aftershock sequence peaks immediately. The big one hits, and everything after. It is smaller and less frequent as the fault settles down. This one opened with 2 magnitude 3.2s, ran for 4 days, and then produced its largest earthquake. That's backwards. That's the signature of a swarm, a sequence driven by something progressively loading the fault rather than one patch breaking and its neighborhood readjusting. And the pattern gets more interesting from there. Central California shakes constantly, so to know whether 5 or 6 days of earthquakes actually means anything, you have to know what a normal week looks like in the same box on the map. Between January 1st and August 7th of this year, 218 days, that box produced 313 located earthquakes, or 1.44 per day. That's the baseline. That's Pinnacles being Pinnacles. The swarm produced 59 located earthquakes in 6 days, 9.83 per day. The fault is running at roughly 6.8 times its own background rate. That's not a rounding artifact or a statistical wobble that disappears if you draw the box differently. It's a large, clean, sustained change in the behavior of a specific piece of the San Andreas over the better part of a week. One more thing about that number that most coverage skips entirely: the catalog is not the fault. A great many small earthquakes in Central and Northern California get recorded on instruments and never make it into any published catalog at all. Detection algorithms have magnitude and quality thresholds. Analysts review only a prioritized subset in areas with denser instrument coverage. Simply publish more small events than areas with sparser coverage. So 59 is not a measurement, it's a floor. Whatever this swarm actually did, it did more of it than the number says. The second strange thing about this sequence is its shape. If a single stuck patch of fault breaks and then adjusts, you get a tight ball of earthquakes clustered around one point. That's not what happened here. The activity resolves into 3 separate clusters spread along roughly 35 kilometers of the fault trace. The main cluster sits 4 to 8 kilometers northwest of Pinnacles, at depths between 300 meters and 5.5 kilometers, and that's where the magnitude 3.94 and the overwhelming majority of events are. A southeast cluster sits 7 to 11 kilometers on the other side of Pinnacles, deeper, 4 to 8 kilometers down, with magnitudes topping out around 2.5, active over 3 separate days. And a northwest cluster up around Trespinos and Ridgemark is deeper still, 6 to 12 kilometers down, active over 2 of those days. 3 clusters, 3 depth ranges, overlapping but not identical. Timing. That distribution is far more consistent with something moving along the fault than with one stuck patch failing in place. The depths point the same direction. One earthquake that Tuesday morning located at a nominal depth of essentially 0, at or just above sea level, datum, which in that terrain means effectively at the surface. That matters because the shallow upper crust on this fault is precisely the part that's supposed to be sliding freely, the part that cannot store elastic strain, and it's where the largest earthquake of the entire sequence nucleated 4.5 kilometers down. To understand why any of that is genuinely interesting rather than just a curiosity, you need one number. The San Andreas Fault, over geologic time, slips at roughly 34 millimeters a year, give or take a few. That figure comes from both geologic mapping and satellite geodesy, and it's about as solid as anything in this field gets. It's the rate the plate boundary demands. The creeping section slips at 26 to 33 millimeters a year right now, continuously, measurable, with instruments planted directly across the fault trace. Those 2 numbers are almost the same, which means there's essentially nothing left over. On a locked fault, the difference between the plate rate and the observed slip rate accumulates as elastic strain in the rock, and that stored strain is what a large earthquake ultimately spends. On the creeping section, that difference is close to 0. There's no strain bank. There's nothing to spend. That single arithmetic comparison is the entire scientific basis for calling this segment safe. And it's not a weak argument. It's the reason the official California hazard model, the third Uniform California Earthquake Rupture Forecast, was genuinely controversial when it included a branch allowing a through-going rupture to cross this segment at all. That branch was added by mathematical necessity rather than by direct evidence. Nobody had ever actually found a trace of such an earthquake happening. Paleoseismologists dug trenches across the central section looking for surface-breaking ruptures and found none in the last 2,000 years. So the case was more or less closed until somebody looked in a place a trench simply cannot reach. Before going down that borehole, it's worth looking at what this fault has already demonstrably done at this exact location, because it's one of the most spectacular pieces of evidence in North American geology, and it's sitting directly underneath the swarm. The rock spires that make Pinnacles National Park worth visiting are the remains of an ancient volcanic field, the Pinnacles volcanic formation. They're only half of it. The other half, the Neenach Volcanic Formation, sits near Lancaster in Southern California, on the far side of the fault. They were once one single volcanic field. The San Andreas cut it in 2 and carried the halves apart. The separation today is roughly 195 miles, 3 times 14 kilometers, accumulated over about 23 million years. That correlation was published by geologist Vincent Matthews back in 1976, and it remains one of the foundational demonstrations that continental scale strike-slip displacement is real, which is the essential context for everything that follows. This fault isn't a crack. It's a machine that has physically moved half a volcano the length of California, and the part of it, under Pinnacles, has been chewing through moderate earthquakes on a generational schedule for the entire time we've been watching. 1949, magnitude 4.7. 1951, 5.0. 1986, 4.8. 1988, 4.7. 1995, 4.9. In August of 2011, a magnitude 4.6, about 600 meters from where Tuesday's earthquake was nucleated, almost exactly 15 years earlier. By that record, a magnitude 3.94 here is unremarkable. 61 earthquakes of magnitude 3.5 or greater have been cataloged in this box since 1990, roughly 1.7 a year. Uncommon, but not rare and not unprecedented. Everything so far says this swarm is nothing. Now here's the part that doesn't fit quite so neatly. At Parkfield, at the southern end of the creeping section, there's a hole in the ground 3.2 kilometers deep, drilled directly into the San Andreas Fault. It's called the San Andreas Fault Observatory at depth, built specifically to answer what an active fault is actually made of. In 2022, a team led by Genevieve Coffey, then a graduate student at Columbia University's Lamont Doherty Earth Observatory, published a study in the journal Geology based on cores pulled from that borehole. They analyzed a band of badly disturbed sedimentary rock lying between roughly 3,192 and 3,196 meters below the surface, 4 meters of rock in total. The technique they used is the important part. When a fault slips in an earthquake, friction along the slipping surface spikes the temperature by hundreds of degrees for a moment. The heat chemically alters organic compounds in the surrounding rock permanently. Measure how far that chemistry has been driven, and you can back calculate roughly how much the fault moved and therefore roughly how large the earthquake was. The method had already been tested on faults in the northeastern United States, in Alaska, and offshore Japan before being applied here. Those 4 meters of rock contain the signatures of more than 100 earthquakes. In most of them, the fault moved more than 1.5 meters, about 5 feet. A slip of that size corresponds to an earthquake of at least magnitude 6.9, the scale of Loma Prieta in 1989 or Northridge in 1994. The researchers noted that many of them could have been even larger, since the method for estimating magnitude from slip distance is still being refined. A second technique, potassium-argon dating, exploits the fact that frictional heat drives argon out of nearby rock and effectively resets its radiometric clock. Those reset ages came back as young as 3.2 million years, which is an upper limit, not an actual age. It's the oldest these ruptures. Could be, not the youngest. Coffey has said publicly that some of these ruptures could have happened as recently as a few hundred or a few thousand years ago. More than 100 major earthquakes, preserved in 4 meters of rock, on the exact segment of the San Andreas that isn't supposed to be able to produce one. This is where the story becomes genuinely contested, and it deserves to be presented from both sides properly, because the way this finding has circulated online since isn't quite what the researchers themselves said. Coffey's own framing is careful. This means we can get larger earthquakes on the central section than previously thought, and there should be an awareness that it isn't always just continuous creep. Morgan Page, a seismologist at the U.S. Geological Survey and a co-author of the official California Hazard Assessment, put it more bluntly, noting that the creeping section is a genuinely difficult place to do paleoseismology in the first place, because the constant creep itself erases the evidence a trench would normally look for. Well, on the finding itself, she said that if it holds up, this is the first evidence of a big seismic rupture in this part of the fault. Page has also acknowledged the consequence. If a large earthquake can tear through the creeping section, it becomes possible, in her framing a remote possibility, for a rupture to start at the southern tip of the San Andreas, run through the middle, and continue to the northern end. That scenario is the one people mean when they say, the big one. Then there's William Ellsworth, the Stanford geophysicist who has led research at the drill site, and his point is the necessary counterweight, the part that tends to get left out of the viral version of this story entirely. His position, put simply, is that most earthquake scientists think these deep time events happen rarely, because tectonic strain isn't currently accumulating at significant rates along this segment, if at all, at the present time. Read that carefully, because he's not disputing the biomarker findings themselves. He's making a narrower, more important distinction. A fault releasing its strain by creeping is not, right now, banking the strain a great earthquake would need in order to happen. What the rock core actually records is what this fault has done across geological time under conditions nobody can currently reconstruct, not what the fault is doing this particular month or this particular year. That distinction disposes cleanly of the claim that's been circulating alongside coverage of this swarm, the idea that a magnitude 3.94 at Pinnacles means the big one is coming. It doesn't. A moderate earthquake in a shallow swarm on a creeping fault does not measurably change the probability of a great California earthquake. Stephen Cox, one of the study's co-authors, put it directly. People should not be alarmed. Building codes in California are now quite good, and work like this exists specifically to figure out what the biggest possible event actually is, so everyone can prepare accordingly. Both things are true simultaneously. This swarm is almost certainly nothing, and the fault it's happening on is not entirely the fault everyone thought it was. To see why that distinction matters in practical terms, follow the creeping section southeast to where it ends. Parkfield, California, a town of about 18 people, is arguably the most heavily instrumented piece of ground on the planet, sitting exactly at the transition point where the creeping section hands off to the locked San Andreas. It produced one of the most famous experiments in the history of seismology. Parkfield generated moderate earthquakes, magnitude 6 or thereabouts in 1857, 1881, 1901, 1922, 1934, and 1966, an average interval of about 22 years. That was close enough to a schedule that, in the mid-1980s, the Geological Survey formally predicted the next one would arrive before 1993, wired the entire area with instruments, and waited. It didn't come in 1993. It came in 2004, 38 years after the previous one, more than a decade past the outer edge of the prediction window, and when it finally ruptured, it broke in the opposite direction from the previous events. That failure turned out to be one of the most useful things that ever happened to this field, because it ended the idea that faults keep appointments, and it's the direct reason the borehole exists at all. If you can't predict an earthquake by watching a fault from the surface, the next question becomes what the fault is physically made of. So they drilled into it and pulled out rock, carrying the record of 100 ruptures nobody knew about. There's one more reason Parkfield matters to this swarm specifically. Slip in the middle of a creeping segment transfers stress toward the ends of that segment. The northern end is San Juan Bautista, where the 1906 San Francisco rupture terminated. The southern end is Parkfield, where the fault locks up and continues into the Carrizo Plain, the reach that produced the Fortu. Tejon earthquake of 1857, estimated near magnitude 7.9. So any accelerated slip near Pinnacles incrementally increases the load at both terminations. To be precise about the scale of that effect, it's tiny. It happens continuously, whether or not there's an active swarm, and no responsible reading of this data makes Tuesday's earthquake a trigger for anything specific. But the mechanism itself is real, and it's the correct answer to why anyone should care about a magnitude 3.94 at all. And that leads to the inversion sitting at the center of this whole story. While Pinnacles was producing 59 earthquakes in 6 days, the Bay Area recorded 11 in the same week, essentially all below magnitude 2.1, with almost nothing happening on the northern San Andreas itself. Southern California produced nothing above magnitude 2.5 on the day of the swarm's peak, just a single magnitude 1.5 near the junction of the Garlock and San Andreas. Faults and little else. Meanwhile, the southern San Andreas and the San Jacinto Fault have both been assessed at a 1,000-year stress high. The Coachella Reach hasn't produced a major earthquake since roughly 1680, 3.5 centuries of quiet on a fault that continues moving at plate rate the entire time. Put those two facts side by side. 59 earthquakes in 6 days on the creeping section is strain actively leaving the system. 340 years of silence on the Coachella Reach is strain entering the system every single day without any release at all. The part of the San Andreas that shakes constantly is the part that essentially cannot hurt you. The parts that could genuinely kill tens of thousands of people don't shake at all. Seismicity is a measure of release, not a measure of danger, and the version of this story that treats a busy week at Pinnacles as some kind of warning sign has the underlying physics exactly backwards. There are 3 specific things worth watching over the coming weeks, and all 3 are answerable using public data as it comes in. The first is whether this patch delivers something larger. The 2011 earthquake, magnitude 4.6, sits 600 meters from Tuesday's hypocenter, and this patch's documented history runs as high as magnitude 5.0. The sequence was still active at a reduced rate days after the peak. Whether the magnitude 3.94 was the peak of the sequence or a foreshock to something larger can only be answered by looking backward once more data accumulates, but the catalog will answer it within days either way. The second is the creep meter record. The most likely explanation for this entire sequence is a shallow creep transient, an episode where a stretch of the fault slides faster than its long-term average for days to weeks, loading the small stuck patches embedded within it and causing them to fail in sequence. That would explain the 4-day buildup, the spread across 35 kilometers of strike, and the shallow depths all at once, and it's directly testable. This segment has been monitored by creep meters and alignment arrays for more than 3 decades. If a creep event gets confirmed for this period, the swarm has a clean explanation. If the creep meters show nothing unusual, the alternative, a locked patch inside an otherwise creeping fault keeping its own generational schedule, gets meaningfully stronger as an explanation. The third is direction. That southeast cluster, 7 to 11 kilometers beyond Pinnacles, was active across multiple separate days. Whether the sequence stays roughly where it is, dies out entirely, or migrates downstrike toward Parkfield is likely the single most informative thing the coming weeks of catalog data can reveal. One footnote worth mentioning before closing out. Almost exactly 28 years before this swarm on August 12, 1998, a magnitude 5.1 struck 10 kilometers southwest of Ridgemark, at the northwest end of this same system. That's a coincidence and nothing more, but it's a useful reminder that the segment everyone has largely agreed to ignore has, in fact, been busy the entire time. The creeping section isn't really a barrier. It's a description of how 150 kilometers of the San Andreas happens to be behaving at this particular moment in geological time. 4 meters of rock from a borehole at Parkfield say it has behaved differently before, at least once, and possibly more than 100 times. The catalog from this swarm is still being written, and it's the thing worth watching closely over the next several weeks. Not because a small earthquake sequence at Pinnacles is dangerous on its own, but because the segment producing it turns out to have a history considerably stranger than the label harmless ever really captured.